I'm holding the presentation today to guide you through the critical design considerations for kHz oscillators and introduce RTCs as an option to solve several of these design issues. So first, get started with a short introduction. When we speak about Epson, which I'm representing here, the company behind is Seiko Epson Corporation. Seiko may be known from wristwatches, Epson from printers, projectors, being market leader in that market space, which obviously is the biggest portion of the roundabout 8 billion euros turnover, which the company makes worldwide. And we in the micro device area are within Epson, Seiko Epson's manufacturing related and variable division, which counts overall for 16.1% of the corporate turnover. And here Epson has a very strong focus on implementing in the products, in the finished goods, as many of the own technologies and products as possible. And as such, the component business, which I'm representing, has been derived out of. Epson is a company with 81 group companies all over the world. And as said, I'm representing the timing device for the European area. One speciality is, as I just mentioned before, that Epson tries to do as many things internally as possible. And that means for our timing device area that we are not only fabricating the crystal material itself, so the crystal blocks, plus then the resonating device, the crystal chip, but as well the semiconductors which are required for SPXOs, for example, so for oscillators, for TCXOs, and other components. So you may be aware that back in 2019, there was a fire at a semiconductor factory over in Japan, which hit the market for TCXOs very badly. And Epson was one of very few suppliers who could still supply TCXOs at that time, so temperature compensated oscillators, because we are using our own semiconductors in-house. So for secure supply, that's a very important topic and advantage. So starting with the actual topic of kHz crystals, the basis is resonating device, which is a so-called tuning fork crystal. So here on the left side, you see how that tuning fork is oscillating. The oscillation is determined by the relationship between the width and the length of this resonating arm. And the electrical equivalent circuit is shown here on the bottom. So it's a resonating path based on this L1, C1. R1 is the ESR equivalent serial resistance, so that's the loss of the crystal, which has to be overcome by the oscillator. So that's the part which absorbs the energy. And C0 is a parasitic capacity, which comes basically from the package of the device, and that parameters are important for one or the other specification of the timing device of the kHz crystal. The important thing is that the kHz crystal has different specification parameters. And one, of course, is the initial tolerance. And the second one is frequency temperature dependency. Even though kHz crystals or crystals overall have smaller temperature variation than other materials like semiconductors or anything else, it does have a certain temperature characteristics, and this is shown with the blue bar here. So the blue bar shows the temperature dependency of the frequency tolerance of a kHz crystal. The red arrows show the initial tolerance, which basically means that that temperature dependency curve is moved up or down depending on the actual tolerance of the individual device. And then there is an additional thing in this equation, which means that due to production tolerances, this blue bar, the frequency temperature characteristic, can move to the left or right, typically by plus minus 5 degrees C. And that all ends up in a certain additional tolerance over the whole operating temperature range. The speciality about kHz crystals really is that the specification is, unlike in megahertz crystals or oscillators, showing only one frequency tolerance specification, which is called here FTOL, So the frequency tolerance standard in brackets, which is the frequency tolerance at room temperature. So only specifying this red bar, the tolerance at 25 degrees C. The frequency temperature characteristic is determined and defined with the two other specification points, the turnover temperature, which typically is this 25 degrees C plus minus 5 degrees C, and a parabolic coefficient, which defines this blue curve overall when going into the formula which is below. Only with this calculation, which depends on the TI, here means the turnover temperature, so this 25 degrees C plus minus 5 degrees C, and this sigma x means the temperature at which you want to know the tolerance. So basically you would determine this with using the extremes of your operating temperature range, like 85 degrees C, and then putting this into the formula. Then you end up with the tolerance, is the frequency temperature tolerance, which the system can obtain. This is something which is very often overlooked because of the way of specifying a kHz crystal. Lots of designers consider only this initial tolerance at room temperature, and the frequency temperature dependency is very often forgotten. But as you see on the graph, even if we look at minus 30 degrees C or 75 degrees C operation, you end up with like 120 ppm frequency error plus the initial tolerance, which is quite significant compared to the 20 ppm initial tolerance. Then there are additional things when you use a kHz crystal. This is passive device which doesn't do anything on its own. It only starts operating when connected to an oscillation circuit. And here there are quite some things which have to be considered and taken care of. And one thing, for example, is shown here. That's the so-called load capacitance. So on the left top, we show the parameters or the function blocks, the components which the oscillation circuit needs to have. And right next to it, we show certain characteristics of the timing device of the kHz megahertz crystal, which is the load capacitance dependency. So when we talk about load capacitance, that's the capacitance which the oscillation circuit has when looking into the pins of the crystal. So taking the crystal out of the circuit, looking into the pins of the circuit, and the capacitance which is there is the so-called load capacitance. And kHz and megahertz crystals as well have a characteristics that if this load capacitance changes, the frequency changes. So if the load capacitance is higher, the frequency goes down, and if the load capacitance is lower, the frequency goes up. If you have the CDCG, so these two capacitors which are mainly determining the load capacitance of the circuit, are discrete components or even implemented in a semiconductor, they naturally have a certain tolerance, and that tolerance means that a 7 picofarad load capacitance trimmed crystal is not operated always at 7.0 picofarad load capacitance in the circuit, but at different load capacitance values, and that means that there is an additional tolerance on top of this 25 degrees C tolerance, this initial tolerance mentioned before. And the graph here on the right top, for example, shows some examples of one of our devices. So if you have a 20 ppm specification for the kHz crystal and you operate this at a 7 picofarad load capacitance, and you have a 7 picofarad load capacitance trimmed crystal, then you will end up with a 0.5 picofarad tolerance on that load capacitance. You end up with plus 39, minus 33 ppm tolerance at room temperature. So that means the initial tolerance specified in the datasheet of the kHz crystal is only valid at the nominal, at the typical load capacitance it is designed for, but in the actual circuit, due to tolerances of the circuit, you will end up with a higher tolerance. And that additional tolerance is higher as lower the low capacitance value is, as you see in this example, going to 12.5 picofarad with 0.5 picofarad tolerance, you end up with plus minus 25 ppm instead of plus 39 minus 33 ppm at 7 picofarad. So in other words, there is a compromise, and this is a very important compromise for the designer of the circuit to be taken. This is shown here on the right lower side. The designer has to decide when going to a smaller low capacitance, you have a safer oscillation start. So the oscillation circuit is more certainly able to start exciting the oscillation. You have a quicker startup time, so the oscillation starts faster. But the issue is that with low load capacitance values in the circuit, you have a higher tolerance. So that is a compromise which the designer of the circuit needs to take based on the requirements of the circuit and the application. There is one trick which I quickly want to announce to check this oscillation startup allowance, so how safely the oscillation is going to start up. This is in this circuit, if you replace this small R called resistor with a potentiometer, you trim it to the max, and then you slowly reduce the resistance of the potentiometer till the oscillation starts up oscillating, and then you measure that potentiometer reading, so the resistance, and that value which you read out there should be 5 to 10 times more minimum than the maximum loss of the crystal, so this R1 or ESR, so the electrical serial resistance of the crystal. And that means the oscillation is supposed to be starting quite safely. In many designs, especially with low power semiconductors, that oscillation startup allowance of a factor of 5 or 10 is very often not obtainable, and that means it's very difficult to assure that the oscillation is safely starting in all 100% of your produced devices. And there are cases where oscillations are not starting and the device fails in production. There are other parameters like drive level. This basically means the energy which goes into the crystal. This measurement requires to measure the current flowing into the crystal. And when we talk about kilohertz crystals, we talk about such small currents which you can't directly measure. You need current probes and special circuitry to measure this. So this is something which basically is very difficult, and for that reason Epson provides and offers the service of board evaluation so that we do this measurement in our laboratory over in Japan. These are just a few of the main topics, or the main topics which have to be considered when doing a kilohertz design. And as mentioned, we see more and more customers facing issues in the actual design based on low power microcontrollers, and for that reason RTC modules are an option for many customers to overcome some of that obstacles and limitations. RTC module means there is a crystal, there is a semiconductor, so using both of our Epson components in one package. The package is typically a MSL1 ceramic package, so it's watertight basically, and the semiconductor has different features like clock, alarm, timer. So keeping the time, it has an interface, typically I2C, but it can be as well some SPI interface. And in our case, we add additional features to this RTC modules, which give some additional value in the circuit of the customer. And with that presentation, I just quickly want to show these options as well. So the cheapest option, of course, is the one on the left top. To realize this RTC function, this is what we just talked before. So you have a crystal and you have the microcontroller. The microcontroller has an RTC function block inside, but in this case, you need to take care of all these kilohertz oscillation design issues, which we mentioned before. When going to the left bottom, you have a dedicated RTC IC. So not using the RTC function block inside the microcontroller. Advantage here is that is a lower power consumption offering. And on the right side, that's what we as an Epson offer as an RTC. That's an RTC module combining the crystal and the RTC chip in one package, which has, as mentioned before, an MSL1 ceramic package typically. So that means it's very safe, it's highly reliable, so it cannot be distorted by some dust, moisture or whatever, like the other two options. So if you have moisture, dust in your application, a kHz oscillation runs on that low power that it very likely is distorted by any environmental change like dust and moisture. This integration has an additional advantage that you can trim the semiconductor to the actual characteristics. So this FTC curve of the kHz crystal, which mentioned before, but I come to that in a second. So here, again, to recap what we had before, so this green curve now is the frequency temperature characteristic. You have the green curve moving left, right, and up, down, as mentioned before. And when integrating the semiconductor together with the crystal, it is possible, and that's what Epson does for many of our RTC modules, there is the possibility to train the semiconductor the actual characteristics of that individual kHz crystal, and therefore compensate for the initial tolerance and this frequency temperature curve. And with that, we can reach this blue curve. And on the bottom, you see a few of that tolerances. So for example, in the operating temperature range from -40 to 85 degrees C, we can reach up to 3.4 ppm, which is 9 seconds a month accuracy. And the way how to reach this accuracy, basically there are two options. One option is to trim the crystal, so to change the load capacitance of the circuit. That's typically what Epson's doing in the RTC modules. The advantage is that the frequency output, all these real-time clock modules, do have a frequency output, which allow to output this 32.768 kHz in order to clock microcontroller, some other devices or whatever. And in case of trimming the crystal, by changing the low capacitance, we actually have a temperature compensated frequency output. The other option is that there is the temperature compensation circuit just manipulating the divider. So the 32 kHz crystal is divided 15 times by 2, and then you end up with a 1 Hz signal, which clocks the second counter in the real-time clock module. And this second option here on the left, on the right bottom, is actually showing that the temperature compensation circuit just accesses one of these dividers, so adding clocks there. But that means that the 32 kHz clock output is not temperature compensated in this case. But as I said, Epson is using the trimming of the crystal, so having temperature compensated frequency outputs. Here on the bottom side, this is just a graph showing what ppms means in second error. So the initial tolerance 20 ppm of the crystal at room temperature means 52 seconds per month on frequency error. Considering then as well this load capacitance topic, so the tolerance of a low capacitance, you may end up in the range of 83 seconds roughly. And if we add into our consideration the temperature variation in a typical circuit from -40 to 85 degrees C, you may well end up with like 591 seconds error a month without compensation. If you compensate the room temperature tolerance, you still end up with 508 seconds. And if you even compensate the typical frequency temperature curve, so not this left-right shift by 5 degrees C, you still end up with 70 seconds a month, so quite significant. And only this integration of the crystal and the RTC chip and the individual measurement, and we do measure every single real-time clock module with temperature compensation at 5 temperature points. Only then you reach this ±3.4 ppm mentioned before. An additional advantage I mentioned before is the low power consumption. Low power consumption here really means that the RTC IC is trimmed for extremely low power consumption. It's not trimmed like a microcontroller to handle megahertz, whatever, 16 megahertz or whatever clock frequencies. So the maximum frequency our real-time clock module sees is the 400 kilohertz for the I2C bus. So it's an extremely low power system, trimmed for low power, and therefore is less power hungry in operation than the RTC module function inside a microcontroller, even in the deepest sleep mode. Then on top of that, we implement features like power switching. That means if the main power fails, the main power which is connected to the microcontroller as well, then some RTC modules have this voltage detection inside, so they recognize if the main power fails, and then the RTC module switches independently over to a backup source, which can be an EDLC, so a supercap, a capacitor, coin cell, whatsoever, in order to bridge certain power failures times. This is very often used in like electricity meters, gas meters, point of sales terminals, and many applications. Another feature which we implement in some of our RTC modules is a reset output. So that means if the supply voltage drops below a certain threshold, we output a reset signal for the microcontroller, so to avoid the microcontroller destroys or interferes with any other circuitry in the application. One more function which we implement in some of our RTC modules is the so-called timestamp or event recording feature. That's a function which detects if an output signal is changing. So we have input pins in this case. If the signal on this input pin changes because there is a door, a case or whatever opened, then we timestamp this event. So we recognize which event happened at which time and date. This is very often used for safety reasons, for guarantee reasons, for surveillance cameras, for smart meters, to see if the circuit has been manipulated, for example. Another function is the so-called wake-up timer. So beside alarm, which triggers an interrupt, for example, when we say, whatever, Saturday morning, 8 o'clock, please cause the interrupt, initiate the interrupt in order to wake me up. Timer means in this case, we can set the timer to reoccurring events, so that like every minute, the timer generates a reoccurring interrupt to wake up the microcontroller to do some measurement, so that the microcontroller can go into the deepest sleep mode during the inactive times till the next interrupt comes. And that overall in many applications saves power because the microcontroller can be put into a deeper sleep mode. For RTC modules, we have different support tools. So we have Linux drivers, we have all the documentations on our internet. We do have adapter boards because the parts are very small, like 3.2 by 2.5 millimeters casings with more than 8 pins. So in this case, it's difficult to assemble this if you don't do the regular reflow soldering. So in this case, we have adapter boards which allow easy access, and we have further support people at Ineltech, at Epson. We are happy to support if you have any questions for them. Here, lastly, this will be in the documentation. There is the overview of the different RTC modules, the latest ones, which are the highly promotion items with the related power consumptions, accuracies, and additional features which I briefly explained before.